Friday afternoon. You're all here. You're all geeks. It's okay. As you're thinking about this, everybody's worried about the economy, and everybody's looking at what happens in the stock markets, and everybody's looking at what happens in Greece. But most of the world doesn't understand what you understand. And what you understand is that there's a second wave behind this financial crisis that is far more important and powerful than anything that's going on in the stock markets. That wave, of course, is this wave of technology. And regardless of what happens to specific companies, to specific industries or countries, this wave of technology is going to continue washing over. And you can do two things with this wave. You can either catch it, or you can be drowned by it. But it's going to happen, and nobody's going to stop that wave. And that wave, I'm going to try and explain it in one of its iterations, which is life sciences, with three very simple ideas. So all of my talk is three simple ideas. The first idea is that all wealth comes from code. You all know that. The second idea is that code keeps evolving. And the third idea is that we're moving from life code from reading life code to copying life code to writing life code. And those are three fundamentally different things. So let's start with the first thesis. All wealth derives from code. The real difference between ourselves and animals is actually very small. If you take the DNA in a human, in each of your cells, that DNA is about 3.2 billion letters. And if you put the DNA of a mouse next to the DNA of a man, the difference is only about 5% of gene code. So a man and a mouse differ by about 5%. Almost every wife already knows that. But as you're thinking about the real difference between ourselves and whales that sing, or monkeys that can learn a sign language, or parrots that can learn words, the real difference is we are the only species on Earth that systematically communicates data, code, to our great-grandchildren. There is no animal on Earth that will do a painting that looks like this. And when you do a painting that looks like this, you can tell people, look, this is how we dress. This is how many of us there are. This is how you have a baby. These are the musical instruments we use. These are the fish we eat. This is how we cook them. So you're learning a lot about Argentina 2,000 years ago because we are the only species that codes. We're the only species that transmits data across time. And as we get better at coding, we generate wealth. So this code becomes this code. Right? Two very important things have happened here. The first thing is this code has become standard. Everybody in Upper Egypt and Lower Egypt can read these hieroglyphs which say Paris. And as you're thinking about what it means to have a common language, and second, even more important, to make that language portable across time, because you can put this on papyrus, you can put this on a clay tablet, and you don't have to go to the cave wall. See, in cave wall civilizations, you have to move to Dordogne to look at the paintings. But when you can put it on papyrus, when you can put it on a clay tablet, you can move it from Upper Egypt to Lower Egypt, to the Phoenicians, to the Babylonians. And when you can move information, then you move from a tribe into an empire. An empire has standard language, standard text, and it can move that text so it can have military doctrine, it can have a holy book, it can have textbooks, it can have contracts, it can have a customs union, because the language has become standard and portable. That, of course, becomes a language that looks like this, and all of a sudden you have a few dozen letters and all human knowledge. And as you're thinking of the implications of all this human knowledge in movable type, you have huge libraries of data. You have huge amounts of code transmitted across countries, across time, across universities. We have big education systems. We have huge archives of data in our companies. This changes religions. This changes business. This changes some countries and makes them rise and some countries fall. Until people come up with your language. And what this language 30 some odd years ago did is it standardized every letter in the French alphabet, every word written and spoken, into 2 letters. And English and Chinese and Japanese and Cyrillic and Aramaic. Every alphabet on the planet is now in 2 letters. But it wasn't just the written word. the spoken word, it was also every photograph, every video, every film, every bit of music, and every tonal scale. And that's incredibly important because a two-letter alphabet can transmit every bit of knowledge in the largest library in France into every French classroom in a few seconds. You better change the way you educate your children. You better educate people differently as code changes. And very small changes in code make a big difference. If I pull out my BlackBerry or my phone and I send you the first line of code, you will get a message that says, "I love you." If I'm in a bad mood, then the second message arrives and it says, "I hate you." So the difference between love and hate is whether you get green or purple. And as you're thinking of the consequences of that, why weren't we using this code if it's so damn effective? Well, because this was 5 megs back in 1956. Right? So you take a single picture on your cell phone, you just used up $1 million worth of memory. Probably not very effective to use digital code, except that the power doubles every 18 months and halves in price. So when you have a system that works like that, it looks really inefficient, really inefficient, really inefficient, and then you get something that looks like this, which is the first computer on the planet that did 1 trillion operations per second. Now, the interesting thing about that is this remained the most powerful computer on the planet for 4 years running, which is really unusual in the computer world. Usually you get these things doubling and doubling. This remained the most powerful computer for 4 years. About 3 months ago, I introduced a new Intel chip. It looks like this. It's about the size of a euro. The interesting thing about this particular chip is you can put them together, you can plug them together like Legos. And if you plug 2 of these together, then you've got computing power equivalent to this. Right? So 2 of these chips, the size of a euro, do 1 trillion operations per second. And oh, by the way, you can put together 256 of these chips in a single blade, which means you can be carrying around 128 terabytes of computer power per blade. When you think of the consequences of that in terms of language and in terms of use, when you think of what it means to have about 2.3 billion transistors per chip, then you begin to understand most of the wealth that's been created over the last 30 years. Almost every large business created over the last 30 years has to do with the application of this digital code. This is where Microsoft and Google and eBay and YouTube and Time Warner CNN and all of these mergers and all of these new companies and all of this new restructuring looks like. You look at the companies that have been growing in Europe, you look at the Nokias, you look at the Ericssons, you look at the Alcatels, you look at the Oranges, you look at this, that, the other. Most of the companies that have grown aren't the cement companies, aren't the traditional steel companies, unless if they come from the developing world. It's the companies that have to do with the management of information. If you look at the countries that have grown, if you look at where employment has skyrocketed, if you look at the countries that are growing 10, 12, 14% per year, there are countries like India, which didn't have a lot of money, but had a centerpiece in a university in the India Institute of Technology, and had a series of programmers that applied digital code that built Bangalore. It's China, it's Singapore, it's Taiwan, it's Korea, it's generations and countries that begin to apply this new code in such a way that you can generate an enormous amount of wealth. If there's one idea that I want you to take from this talk today, it's that the code that you are all working with is shifting again. And in the same way as we move from hieroglyphs or cave wall paintings into ABCs, into movable type, into ones and zeros, we are now moving code again. And the dominant code is evolving, and it's evolving in this way. So in 1953, Watson and Crick started to argue that all life forms on this planet, every orange, every apple, every clover, every sheep, every dog, every bacteria, every human being, every politician, are all made of the same thing, right? And they called it DNA. So this is a spiral staircase with a series of rungs. It's adenine, threonine, guanine, cytosine. And as you think of the consequences of all life being coded in 4 letters, you begin to understand life as code. And if you put that DNA into these gene sequencing machines, then you can write incredibly boring books that look like this. Right? If you think the code books are boring, the DNA books are just stupefying. Because a single machine about the size of a large computer today will generate about 100 billion letters of that code per day. Oh, by the way, these are becoming the world's largest databases. These things are accumulating about 37% faster than computers can be built to keep up with this information. And we're going to have a crossover point where the data generated by biology cannot be stored in computers, because this system is growing 50% faster than the digital revolution took place. Now, why is this particular life code important? Because it makes this apple a system that executes code. Okay? You don't have to plug it in. You don't have to buy a license. All you have to do is this. And when the apple does that, it begins to execute a code that looks like this. And what it does is it says AATCAAGG, which means make a little root. TCGAA, make a little stem. ATAA, make a series of leaves. GTAA, make a series of flowers. AATC, make a series of apples. Remember those little ones and zeros? 001111, I love you. 01111, I hate you. Same thing happens with this. I change a couple lines of gene code in this orange, or this apple, may become a red apple. It may become a crab apple. It may become a larger apple. It may become a smaller apple. If I change a few more lines of code, it becomes an orange, or a tangerine, or a grapefruit. If I change 1 in 1,000 of those letters right there, you become the person sitting next to you. Be a little bit more careful where you sit next time. But as you're thinking of this stuff and the structure, and the reason why this stuff matters is because it turns out that all life is imperfectly transmitted code. And because it's imperfectly transmitted, you get evolution. And as creatures evolve, you begin to find things like this. Even within the same species, you have absolutely immense variation depending on very, very small changes in code. There's about 23,000 genes inside each of these dogs. It's the same species. If you change a single gene, you get a 200-fold differential in body weight. As you're thinking about the future of production, of agriculture, of a whole series of other things, this is not plugged in for some reason. If we could get a little bit of technical help. I'm not sure why this is not getting power. But anyway, as you're looking at this stuff and the differences between these, this is what a modern gene cloning lab looks like. Okay, this is in Argentina. And after you talk to the scientists, you meet this very friendly cow. This cow has been treated so well, it acts like a dog in a French restaurant. Okay, you come up, you pet it, it's very nice. As you're petting this cow, these two guys show up. And at this point, you have to say to yourself, hey, you know, those two look really similar. And in fact, they look an awful lot like this one. And the reason why is because what scientists did here is they took a cell out of the ear of the cow, and each cell in each of us contains our entire genome, our entire gene code, which means each cell contains our entire operating code, whether you're a cow or a human being. So you can take a cell out of the ear, insert gene code into that cell in such a way that it will make a photocopy of itself. And it will give birth to two clones. This is what gene cloning looks like. This is a veterinarian, left hand way up the back of the cow, holding an ultrasound machine in his right hand. And in the morning I took these pictures. He placed dozens of cloned embryos in cows. Which is why when you walk out on the Argentine countryside today, there's a lot of cows that look really, really, really similar. Because I did not expect to find this in Argentina, I'm running around taking pictures with my digital camera until a very friendly Argentine gaucho shows up and says, "But che, what are you doing? Why are you taking so many pictures?" Can't you understand? They're all the same. This is the third stage of life code, right? So the first stage of life code, we read it. Second stage of life code, we copy it. Third stage of life code, we begin to write it. This cow was born about 2 months after I took those pictures, and this cow is important because they changed the gene code of this cow in such a way that it produces a medicine used to treat cancer in its milk. Every time you milk this cow, it will produce erythropoietin, EPO. 20 of these cows substitute for a factory that's this size. How we make things, where we make things, is going to fundamentally change. This is something on a scale or beyond an industrial revolution or a digital revolution. And as you're thinking of this stuff, you don't even need to have the entire animal because you can execute life code. So you can take cells from a cow to make a cow, but you can also take cells from a mouse to make mice teeth that are growing without a mouse. These are cloned mice teeth growing in a little glass petri dish. Of course, if you can do that with mice teeth, you can also do it with human teeth. Right? So you can make a biodegradable mold of a tooth you lost and grow another one. This should not surprise you, right? You were born with no teeth. Your body knows how to make teeth. You make a full set of teeth. You give them to the tooth fairy. Then a second set of teeth grows. Problem is, if you lose any of those second set of teeth, they don't grow again unless if you become a lawyer. But as you're thinking of the consequences of this, you know how to make teeth. You've done it once, you've done it twice, you can do it a third time. And of course, if you know how to make teeth, you also know how to make ears. So Tony Atala down at Wake Forest is making ears in petri dishes. And of course, if you can make ears, you can make bladders. Which, believe me, if you have bladder cancer, it's a lot more pleasant to regrow your own bladder than to walk around with a plastic bag the rest of your life. Tony Atala is now working on 42 organs. Now, just in case you think this is something exotic that's only taking place in a few places in the crazy United States, here's the latest Harvard Biosystems catalog. So you can get a catalog from Harvard Biosystems, and one of the things you can do is you can go to this page and order your own bioreactor to make hollow organs, bronchial, trachea, or blood vessels at home. Or maybe you'd like to try something more complex. Turn the page. Here is your bioreactor to make whole hearts. So you can now make whole hearts at home on a mouse scale. This stuff is moving very, very quickly, and as it moves quickly, here's an experiment that took place quite recently. This is where it starts to get a little strange. What 2 different Chinese labs were able to do is to take a mouse skin cell, turn that skin cell into a stem cell. See, each of you starts out as a stem cell. Each of you, when your mother and father come together, ovum and sperm, they create a single cell. That is a cell that becomes everything that's you. That cell becomes 2 cells, 4 cells, 8 cells, 16 cells, 32 cells. For the first 16 divisions, that code executes perfect copies of a cell that can become any part of your body. Those are called pluripotent stem cells. After the 16th division, what happens is each of your cells has all of your code, but it only executes a small portion of that code. I'm going to become stomach, I'm going to become eye, I'm going to become bone. But because each of your cells has your whole code, you can take a skin cell, make it a stem cell. And oh, by the way, the stem cell can then become a full mouse. So you take a skin cell, you make it a stem cell, and you give birth to an entire animal. It is now official. Men are useless. As you're thinking of the consequences of this, it has absolutely immense consequences for industrial systems. Because you can program animals, because you can program plants, because you can program bacteria. And you can program these things to make different things. So this is a bacteria that's programmed to make a biodegradable plastic. Instead of going out and finding oil, transporting oil, putting it into a refinery, going through a primary cracking process, a secondary cracking process, a tertiary petrochemical process, you simply program the bacteria to make the plastic. By the way, about 93% of the body weight of that bacteria is a biodegradable plastic. And it's companies like DuPont that are using these things. All of these new fabrics, these stretchable fabrics that don't let water in but let you breathe out, the new types of rugs that are stain resistant, the sneakers that you're wearing, a lot of those are made out of a fabric called Serono that's made in Tennessee out of bacteria. See, DuPont got very tired of paying yo-yoing prices for oil, so it sold its traditional petrochemicals, nylon, rayon, polyester, to Saudi Arabian basic industries, and then started making its new materials in bacteria. It looks like a giant beer factory. By the way, this is not a plaything for DuPont. DuPont has gone from being a chemical company to having 33% of last year's earnings coming out of life sciences. Now, if DuPont was an exception and Monsanto was an exception, okay, then that would be a small sector of the economy that's moving in this way. But here's General Electric. About 14% of General Electric's revenue today comes from healthcare and life sciences, and this is the fastest growing area of General Electric. And as you're looking at IBM, one of the fastest growing areas at IBM is also life sciences because the volume of data is so absolutely enormous in healthcare, in imaging, in life-related technologies. Here's an experiment that we carried out over the last 3 years. Over the last 3 years, a company that I co-founded with the man who sequenced the human genome and the man who won the Nobel for figuring out how to split genes, we decided that we would try and program a cell much as you can program a computer. So we would take basic gene code, assemble it chemically, introduce it into a cell, and have the cell execute that code. About 4 weeks ago, we announced this. So this is the first synthetic cell in the world. And what we did is we built this cell piece by piece. We took a computer, said this is the exact code we want. We then had robots assemble the 4 base pairs of DNA in very long stretches. We then invented a series of technologies to put together those very long stretches of DNA. We built the world's largest organic molecule. Nobody's ever built a molecule larger than this in organic terms. We then invented a series of techniques to insert that code into a cell in such a way that the cell would boot up and execute that code. And by the way, it worked. So this is the cover of The Economist 3 weeks ago. That little cell is the equivalent of the first transistor. It's going to give birth to the equivalent of a Silicon Valley, of very large industries, and of a new way of coding things. It's not that you couldn't do digital code before the first transistor. Babbage had his calculating machines, and people were using abacus, and all kinds of things were happening. But the transistor made it practical and simple to begin to generate chips that would do a lot of operations. It took a long time. You can see out here in the Computer Museum how long it took. But by the time you try and figure out where do all of your businesses come from, where does economic growth come from, what's the future of your businesses are viable and are growing because we had digital code, we understood how to program it, and we had machines to execute it. This little cell right here, which is the first synthetic cell ever made, is that programmable machine. and we know the code, and we know how to execute the code, and we have very, very, very large libraries of data. Is this all delusional? Well, not exactly. We've partnered with little small startups like ExxonMobil to begin to program these cells to make fuel in algae. We have started to program with a series of other companies to begin to make products out of programmable cells. So you will see very large changes in agriculture, you'll see changes in chemistry, you'll see changes in textiles, you'll see changes in vaccines, you'll see changes in biotech, you'll see changes in pharmacy. It's very hard to understand places where you won't see changes. Among other things, an amoeba dubia has 664 billion base pairs in it and needs about 1 billion to live. That is about 200 times the gene code that makes a human being. So a single amoeba has 200 times the bits of a human genome. What does that mean? It means that in a single bacteria, you can code it just as you code digital code. Because you can say A equals 0, 0, T equals 0, 1, C equals 1, 0, G equals 1, 1. And all of a sudden you've merged all of the digital world and all the biological world into the same language. That's called bioinformatics. What practical use could you have of that? It means anything you code as life, you can code as digits. Anything you code as digits, you can code as life. In practical terms, it means you can store every copy ever printed of the Le Monde newspaper on a single bacteria that you can then clone millions of times. Information storage starts to move in very strange directions. Here's what's really important in this story. When you think of where economic jobs come from, when you think about where wealth comes from, when you think about where economic growth comes from, when you think about which countries are going to be powerful, it's not the countries that have the great monuments and skyscrapers. It's the countries that have office buildings that look like this. Among other things, this is the office building where Google was launched. Now, I am thoroughly biased on this because one of the things I do is I'm a venture capitalist, which means we go out and we invest in new companies. But those little companies really matter. In the US, venture capital-backed companies are 0.02% of the entire US economy in terms of investment, but they're 11% of jobs, and they're about 21% of the entire US economy. It really matters in an economy if you have these little startups that become bigger and bigger and bigger and bigger. That's what becomes the Hewlett-Packards, that's what becomes the Microsofts, that's what becomes the eBays and the YouTubes and the Googles and the Netscapes. That's what becomes all of this engine of creation. And if you're able to bridge academia and research and these small businesses, then you will have a prosperous and growing country. If you are not able to establish that bridge, you will have a great history but not a great future. It is absolutely essential in Europe, in France, that you not walk out of here scared of these technologies. Right? What I want you to understand right now is I'm giving you a very small slice of some of the stuff that's happening, and I didn't touch on robotics, and I didn't touch on nanotech, and I didn't touch on imaging, and I didn't touch on a bunch of other things. But we are now at a stage where knowledge is going to double in the next 5 years. Not knowledge, data. And that gives us and our kids this absolutely enormous ability to generate wealth on an absolutely unprecedented scale, to invent entirely new fields, to do things in a completely different way, and to do so in 1/5 of a human generation. But only if we educate our kids, only if we have our universities tied into this engine of creation, only if we have a business sector that can support startup companies and grow them quickly. We have opportunities the likes of which nobody has ever seen to grow things in so many different fields. You don't like this one, try this one. You don't like that one, try this one. But what's really important is that in a country where you did have these individuals that created worldwide brands, that created worldwide companies, were able to have a generation that looks much like what's in this room, that looks much like what Octo's been building, that becomes the next generation of very large global companies that generates jobs on a massive scale and is globally competitive. Because while this is what powered the French economy for some of the past generations, what's absolutely essential is we now have the subsequent companies, and we quit relying just on the car companies or just on the airplane assembly companies or just on the beer companies, but that we take things like this and make the next generation of a cosmetics company or the next generation of a textile company or the next generation of a fashion company or the next generation of a communications or storage or computer or medical or vaccine or whatever the hell you want using this new type of code. And that's why what's going on in this room is so important. Because if there is a future of the French European economy, it looks very much like what's sitting here. You are not going to double the GNP of Italy by making fiat a little bit larger. You are going to double it if you have about 10,000 brains in Italy who are trained in code, be it digital or life code. You've proven that in Taiwan, in India, in Singapore, in Korea. In Korea, the average Korean earned 1/5 of what a Mexican earned in 1975. Today they earn 5 times more, and they have a standard of living that's approaching that of the United States. And it's that bridge, it's that brain power, it's that ability to create and apply code that really matters. And that's why the geeks have to rule. I actually mean that seriously, right? I mean, if we keep depending on the Grande École brains going into the Élysée Palace or into the Louvre and managing the economy, that is managing the pieces that exist. The really important part, alongside managing what exists, which is great, is generating the rest of it, the growth. And in an economy where you have more and more people retiring per person who works, the productivity per person has to go really up really quickly. And the only way to do that is through geeks. The only way to do that is through high-tech companies. The only way to do that is by generating code in a more efficient way than anybody else on the planet. And if you do that, then maybe finally people here will realize that geeks really do rule. So let me stop there and see if there are any questions. Thank you very much.
Hello, Mick Philippon from Octo. Well, one question I have when seeing artificial organs and so on is, what about the experiment on humans, on human genome, on creating human clones or eliminating death and so on?
I think creating human clones is a particularly bad idea. The attempts to make Dolly required 200 and some odd implantations to get one right. Cloning is still a very primitive technology. There are many errors in clones. We don't know what the effect of cloning is across species, across time. So until we understand cloning in a far more systematic and scientific way, it would be, I think, immoral to experiment in cloning on humans. That doesn't mean it's not going to happen, because as of today, at least 27 different species have been cloned. It has become relatively commonplace to clone a whole series of species. People have started cloning their pets because their favorite dog or cat dies. What that means is there's a tremendous incentive for some rogue scientist someplace to attempt to do this on humans and then announce it. But I think that's a mistake because the technology is not there and because that could mean that we would have hundreds of George W. Bushes running around.
Cool. For the first cell made by human, you take the gene you copy gene in. Did you copy the gene from natural bacteria or you create ex nihilo?
So what we did for the first synthetic cell is we took a known genome, the genome of Mycoplasma genitalium, Mycoplasma capricornium, and we assembled the gene bits in almost an identical order, but we assembled it from chemicals outside of a cell. Then we inserted about 4 bits of poetry, which are now part of whatever new cell is there. And then we found a technology or invented a technology to insert that into a cell in such a way that the cell would begin to operate that DNA instead of the DNA in a cell. So let me give you a more practical example. All of biotechnology is inserting a single gene into a cell almost at random and hoping that it sticks. So that's the equivalent of taking a book by Tolstoy and inserting a single sentence and hoping that the meaning of the book changes in a fundamental way. Yes, there are particular sentences in particular spots in that book where the book will change, but boy, you better get the right sentence, and it's going to be hard to do. What we have done is we've written the book from scratch. And that's the big difference. Let me put it in different terms. If I had a Volkswagen parked in my garage, and I built the engine of a Lexus, I could take that Lexus engine, stick it into the Volkswagen one night, and come back 24 hours later, and every bit of that car would be a Lexus. That's what this program does.
Yes, good afternoon. We do have an issue with the bees right now. How does the coding life techniques that you describe apply to this issue, if they do? And in more general terms, how do you tackle the biodiversity issues?
So I'm sorry, you have an issue with the fees? Bees, sorry. You know, there's so many smart people working on bees. They've got to get it right way before we can apply this to bees. It's going to take us years to get from bacteria to far more complex organisms. And we don't have that kind of time with bees. There are far more effective techniques. There are far more interesting ways of beginning to understand the diseases or the chemical impacts on bees than this stuff. I wouldn't hold my breath for this. That's not where you're going to see the first impacts. I'm sorry, there was a second part? Biodiversity. You're going to see a lot more biodiversity. Let me give you one example. Every year, there is a contest held at MIT called iGEM, International Genetically Engineered Machine Competition. And what kids do, and they come from all the universities in the world, including several universities here, is they come together in a jamboree to show other kids what they were able to build in the last year. The only difference is it's alive. So what these kids are doing is they've built the equivalent of a Radio Shack for biology. See, a lot of us got interested in this stuff because somebody gave us a kit that had little tiny holes in it and then little wires and little capacitors and little light bulbs, and you could make a little buzzer, or you could make a little device that would shock your sister, or you could do all kinds of fun things. And that's how a lot of us learned about electronics. There was a little standard kit, and you connected the wires and built a little computer, or built out this, or built out that. These kids are now building a standard registry of biological parts. So you can go and you can get a be subtleist, you can go and you can get an E. coli, you can go and you can get a cell-free system, then you can order bits of DNA, you can order bits of RNA, and you can make stuff. And these kids are making pretty neat stuff. The team from Baylor University decided that they would engineer what makes red wine good for you, resveratrol, into beer. Why that would occur to a college student, I don't know. The team from Tokyo University got a little bit more ambitious. The team from Tokyo University went out and tried to design a bacteria that would do a couple of things. First, the bacteria doesn't freeze. Second, the bacteria doesn't get sunburned. Third, the bacteria can survive extreme changes in temperatures. And fourth, the bacteria likes to eat iron and create oxygen. So it's a factory to make oxygen. That all sounds relatively simple and innocent until you begin to understand that their purpose was to create a colony of these bacteria, to put it in a rocket ship, to shoot it at the ice caps in Mars, and have that bacteria start eating the ice on Mars so it would create an oxygen atmosphere on Mars that would be livable. So they were talking about terraforming a planet in their little biodiversity experiment.
Hi. First of all, thank you for the presentation. It's a bit too mind-blowing for a late Friday, but that's okay. So most of us are IT crunchers. If I follow you, you're saying that this is the new platform, right? This thing is the new platform. We'll be able to build code and maybe store data in the future. How do you foresee that? I don't know. I'm kind of excited of the potential, but.
So look, I hesitate to do this in a room that actually knows what it's doing, but each of your cells has your entire gene code on it, which is at least 6.4 billion bits. So I guess I'd be saying you've got 6.4 gigs inside each of your cells worth of gene code, if that's the right conversion measurement. Then multiply that times 100 trillion cells, which is what your body is. Okay, so that's the processing capacity that you have in your bodies. It's 640 trillion gigs, whatever the hell that is, right? And when you think of that storage capacity in a body this scale, the storage becomes really interesting. But then the I/O, the input-output of this stuff, how you coordinate these 100 trillion cells, how you get the data from here to here, is a really interesting set of questions. And as you begin to think of programming, as you begin to think of shortcuts, as you begin to think of storage devices, as you begin to think of programmable objects, as you begin to think of interlaced, intercommunicating objects, I think beginning to understand how the body executes this code, how the body stores this code, is going to give you a whole series of possibilities of getting beyond the 12 nanometer scale that you're now stopped at in polishing computer chips. And it may allow Moore's law to run forward. But there's a series of more interesting implications. And again, one of the things, look, a lot of people come to me and they say, boy, you're such a good futurist. I'm not a futurist. Okay, I'm not smart enough to tell you what's going to happen. The reason why I use photographs is because that's already happened. I'm a historian. Now, if I were a futurist, then one of the things that I'd be talking to you about your theme, and if I were your age, probably one of the things I'd be doing is, instead of getting mixed up in life sciences, I'd probably be mixed up in brain research. Because I think as you begin to design the next generation of computers, as you begin to think how you're going to execute code, the next generation of computers, to my mind, looks a whole lot more like the internet than it does like a computer chip. Right? And the reason why is because, as all of you know, if you cut a specific node on a computer chip, often the whole damn thing crashes. But what Hewlett-Packard and a series of other people are doing in projects like Teramac is they're beginning to design computer chips so that they become multi-redundant. And if this node breaks, they go to this node, and if that node breaks, they go to this node. Now, the engineers are horrified by this because there's extra connections, because there's workarounds, because it's not always the shortest path. I mean, there's a whole series of reasons why, in traditional engineering building terms, this is really not elegant. But oh, by the way life works and the reason why life is robust is because it's got all these workarounds. And as you begin to design computers that look like the brain, you're going to have these multiple nodes, these multiple workarounds that look a whole lot more, and I think as we learn the stuff from life, they will have direct applicability towards computing, towards coding, towards a whole series of things in really interesting and unexplained ways. I mean, we can't even begin to imagine. This is a little bit like 1970 and somebody saying, hey, we've got this ability to make the small first personal computers and maybe we can begin to connect them. So what? Well, it turned out to be a big so what. Same thing will happen as you have this dialogue between life and computing and design and code.
Do you think it's possible to create weapons with this technology?
To create
Weapons.
weapons.
And what do you think we should do about it?
Okay? So, you know, every once in a while when I get into one of my dark moods, I try and think of a technology that human beings have not used to hurt one another. And it is really hard to do. Right? I mean, when you think of what you can do with a word to another human being, when you think of what you do with steel, when you think of what you do with electricity, when you think of what you do with video, I mean, there is not a technology that I can come up with that someone has not said, boy, I can really hurt somebody with this. This is a really powerful technology. We absolutely have to strengthen the bioweapons conventions and the UN and a whole series of organisms that are against biological chemical warfare. And it's really important we do so, and it's really important we put some teeth into those conventions, and it's really important we do so in the short term. There are risks to any powerful technology, and this is a really powerful technology. On the other hand, one of the things that we keep forgetting is life on Earth, for most people, has gotten a whole lot better in the last 100 years. Even with all the wars that are going out there. We have gone in about a century, over a century, from a 15% chance of dying in a violent something for somebody 15 to about 40, to about 2%. Even with all the problems we've got of hunger in a series of places, we've brought India and China from places that had constant famines into a place where most people are eating, and we have an excess of calories in the world as a whole. They're not equally distributed. There are places that have famines. Even with all the problems that we've got going on, we've gone from an average lifespan in Europe about 100 years ago of 30 some odd years into late 70s. So yes, there's stuff to be afraid of. Yes, there's stuff that we have to take care of. Yes, there are ethical considerations. Yes, this is going to upend religions. It's going to upend countries. But those countries that are afraid of this stuff and say stop the world and try and regulate this stuff have to go back to that first image of that huge wave. That wave is going to come. Now, you can try and stand aside and pretend the wave doesn't exist, or you can be afraid of the wave, but it's a whole lot more pleasant to surf that wave than it is to sit there and be crunched by it. If there are no more questions, then we should let you all go enjoy Friday and drink some wine, which is biotechnology. Thank you.